All right, I'm assuming everything is working perfectly, so let's get started. So last week we looked at brute force algorithms and how they can be used to sometimes solve problems with limited constraints, where the constraints are very low, where the time limit is very high, or where you don't have to deal with too many numbers, so you can simply try all possibilities. This week, we're going to be looking at a little bit more on brute force algorithms, and specifically cases where brute force doesn't necessarily give you the best answer, but it gives you an answer which will score partial marks. So I want you to understand how to write those brute force algorithms so that even if you can't solve a problem in a contest, you will be at least able to get some marks. So how do we do that? So I guess the best way to show you this is to start with a problem. So let's look at this problem that we have here, stacking numbers. Now I must warn you, from here on, the problems I'm going to pick will be a little bit tougher than the problems that we've done so far. That's intentional because the problems are getting harder and they need more complicated techniques to solve. So for this particular problem, brute force will certainly not be the optimal solution, but it is a solution and it will get some marks. So we'll see how it goes. Okay, so here we go. I'll read the problem. It's raining outside, you're bored, and you desperately need something to do. Staring at a pile of soft drink cans in the corner, you devise a game that could keep you entertained for hours. The game is played on a pyramid of side length 6. The pyramid contains 21 boxes as illustrated below. In each box, you must place a single non-negative integer. Okay, so 21 numbers go in these 21 boxes. 6 plus 5 plus 4 plus 3 plus 2 plus 1 is 21. So they're 21 numbers. You may choose the 6 integers that are placed in the bottom row of the pyramid. Okay, so we can choose these ones. Once the bottom row has been filled, you have rules that describe how to fill the remaining boxes from bottom to top. The integer that is placed in the very top box of the pyramid is your score. Your aim is to obtain the highest score possible. Before you play the game, you're given some positive integer b called the base. The rules for filling in the remaining boxes are as follows. For each box below the top row, you add the integers in the 2 boxes directly beneath it. If the sum is bigger than or equal to b, then you subtract b from this total, so the sum becomes strictly less than b. So for example, we have 12 plus 21 here. 21 plus 12 is 33. 33 plus 28 is 61. 61 plus 88 is 149, but we're playing with the base b equals 100, so we subtract 100 to get 49. Okay, 49 plus 50 is 99, 50 plus 48 is 98, and for the topmost row, we have to multiply. So it says for the very top box, you simply multiply the integers in the 2 boxes beneath it. Okay, does that make sense? So every time you add until you get up here, and then you multiply. Now, note that every box aside the topmost box contains an integer between 0 and b minus 1 inclusive. In particular, if the 2 integers beneath a box add to precisely b, then that box is filled in with the integer 0. Okay, so for example, if we get to 100, 100 minus 100 is 0, so we get 0. To make the game more interesting, you are given a small set of numbers from which the 6 integers in the bottom row must be chosen. No integer from this set may be used more than once in the bottom row. You must write a program that selects 6 integers from this set to place in the bottom row so that you obtain the highest score possible. Okay, so let's get started on the problem. So let's take a look at what the input actually contains. So here we have, in this case, this is the input that we dealt with, 100, which is our base, and we have 7 numbers to choose, of which we have to choose 6. So we have 1, 2, 3, 4, 5, 6, and 7, and our output is the best score possible and the 6 numbers that we chose. So in this case, we chose 2, 5, 6, 7, 4, and 3, and we chose them in a particular order. Now the order actually matters, and we will see why. Okay. So let's try and figure out how we can go about solving this problem. So let me get my webcam, my trusty webcam out. Okay, so let's get started. Okay, so our strategy is going to be that given that we have a certain number of choices, we have a certain number of choices for the 6 numbers. So we have some number of choices for the 6 numbers in the bottom row. Okay? So for example, in the example case, we had 1, 2, 3, 4, 5, 6, and 7. Now we need to choose the 6 numbers to go at the bottom, right? And the question is, how do we do it? How do we do it? So our output in this case was, hang on, what was it? It was 2, 5, 6, 7, 4, 3. 2, 5, 6, 7, 4, and 3. So the first thing we should note is that it's not just the numbers that matter, it's the order that matters. So let me try and show you why, okay? So let's actually play this game with, if we have 2, 5, 6, 7, 4, 3, we could do 2, 3, 4, 5, 6, 7, right? So let's start with the numbers at the bottom being 2, 3, 4, 5, 6, and 7. So what we're going to get is 2 plus 3 is 5, 3 plus 4 is 7, and b equals 100. So b equals 100. 3 plus 4 is 7, 4 plus 5 is 9, 5 plus 6 is 11, 6 plus 7 is 13. Whoops, 13. 11 plus 13 is 24. 9 plus 11 is 20. 16, 12. 12 plus 16 is 28. 16 plus 20 is 36. 44. 20 plus 30 is 50. 64. I would assume 30 plus 40 is 70. That's 80. And then the answer is 64 times 80. Okay? So 64 times 80 should be, I think, 5,120. Let me just confirm that. Yes, it is. It is 5,120. So our number at the top is 5120. Okay, now if we take a look at our example case, which I am going to do right now, let me do that. We'll see that we got a score of 9702 with the best combination, 2, 5, 6, 7, 4, 3. So it's not just the numbers that matter, it's the order. The order also matters. Where the numbers are positioned definitely matters. Okay, so what this means is we need to go through, from the choices we are given, we need to go through every possible permutation of 6 numbers. So given the number of choices, let's say number of choices. I think they have a name for this in the actual question. Let's take a look, actually. What do they call it? Here we go, S. The second line will contain an integer S representing the number of integers in your set from which the bottom row must be chosen. So that's the number of choices. So let's call that S. So given the number of choices S, we need to check we need to check S. We need to check all permutations of 6 elements from a set of S elements. S elements. Okay, so what do I mean by this, right? So for example, let's think about 1, 2, 3, 4, 5, 6, 5, 6, 7. Okay. Actually, we'll think about a simpler example. So let's say I have 4 numbers. Let's say 1, 2, 1, 2, 3. Let's say 3 numbers. So S equals 3, and I have to pick 2. We need to pick 2. Okay. So the idea is we can pick 1, 2. We can pick 1, 3. We can pick 2, 3. Right? We can pick, are there any other combinations? I think that's it. Yep, 1, 3, 1, 2, and 2, 3. And we can also permute them. So this has a permutation 2, 1. This has a permutation 3, 1. And this is a permutation 3, 2. Fair enough. So there are 6 ways in which we can pick this. So yeah, there are 6 ways. There are 6 ways we can do this. So now, what does that mean, right? It means that there are six choices that we have. 6 choices that we have in order to do this. And we essentially need to check each of those choices, right? For the 3 pick 2 sort of thing, right? But for the case when we have a lot of elements, let's say in the case 1, 2, 3, 4, 5, 6, 7, we need to choose, first of all, we have to choose 6 elements. Let's say it's 1, 3, 4, 5, 6, 7. Okay, that's a permutation of 6 elements. I mean, sorry, that's one choice of 6 elements from 7 elements. But for each of these choices, we have 6 times 5 times 4 times 3 times 2 times 1 equals 6 factorial permutations. If you haven't heard of factorials and permutations, I'll just quickly run you through it. So if I have, say, 4 numbers, let's say 1, 2, 3, 4, and I want to swap them around, right? The idea is that if I have 4 blank spaces like this, I have 4 places to place the first thing, either 1, 2, 3, or 4. But after I've picked one, I only have 3 choices left for the next box, right? So I only have 3 choices left to pick this, like that. And then once I've picked something, maybe it's this one, I only have 2 choices for the next box and 1 choice for the last box, because we've already decided basically what goes there, right? So when we multiply all of these together, the multiplication principle of counting essentially says that when you have a problem that can be separated into a bunch of individual choices, you can basically just multiply them. So the idea is this is 4 times 3 times 2 times 1, which we call 4 factorial, or factorial 4. Okay. You might have seen this in a discrete math class or something. Okay, that makes sense. So now, one other thing we need to note is how long is this going to take? So we want to go through all permutations of 6 elements from S elements. Okay, so we know that there are, we call this PS6, right? Or the number of ways to pick 6 elements from S elements. And this is essentially 6 factorial times CS6, where C is the number of choices, number of choices of 6 elements from S elements. And if you're familiar with a little bit of counting or discrete math, you might know that this function CNR, right, where we have n elements to pick from, R as in how big is the set of choices we draw. For example, in this case, it's 6. We know that there is an explicit form of this. CNR is equal to n factorial over n minus r factorial, r factorial. Okay? I won't go over this, but you can basically just look this up. Number of ways to choose R objects from N objects. It's pretty simple. You can just go through it in your own time if you don't know this. So PS6 is essentially S factorial divided by S minus 6 factorial, but we have to multiply it by 6 factorial, so we get S factorial over S minus 6 factorial. That's the number of permutations there are. Okay? Now, this, we can kind of simplify this. So we know that n factorial is, of course, n times n minus 1 times n minus 2 all the way to 1. So we know that since S factorial is S minus 1 all the way to 1, we can see that S factorial over S minus 6 factorial is simply S minus 1, S minus 2, up to S minus 5. Okay? So now we have something, right? We need to essentially pick all of these permutations. We have to go through each of these permutations, and for each of these permutations, we have to choose the highest thing with the highest number. Okay, let's try and understand how that works. So let's assume, I'm not going to go through the entire thing, but I will show you how do we find the best score for a given set of numbers. And you might say this is actually pretty easy because all we have to do is simulate the pyramid game. But there is a slightly easier way, which is to hand simulate the pyramid game and then write the result into your computer. So if you have 6 numbers, A, B, C, D, E, F, you can say that this is A plus B mod base, B plus C mod base, and so forth. E plus F mod base, and so forth. Compute this, compute the next 4, the next 3, the next 2, the next 1. And I'll save you the pain, and I will let you know that the top number is A plus 4B plus 6C plus 4D. This is really easy to do on your own. It's a good exercise to do on your own, is to simulate everything up the pyramid and actually check this formula works out. Plus E mod base multiplied by b plus 4c, b plus 4c plus 6d plus 4e plus f mod base. Mod base. Okay, so if we have these a, b, c, d, e, f at the bottom row, the top number is always this. This is key. It's actually really simple to figure out. You just have to literally hand calculate all the numbers until you get to the top of the pyramid. The multiplication comes from essentially multiplying the two numbers in the second bottom row. So remember in the example we had like 99 times 98 equals 9,702. This is our like 99, this is our 98. I hope that makes sense. So now our algorithm kind of suggests itself. Now that we know what permutations are, how many permutations we have to actually go through, right? And we know how to generate the top number, or the number at the top of the pyramid, our score for a given set of the bottom numbers. We can devise our brute force algorithm for this problem. Okay, so let's do that. So our algorithm is essentially to generate all PS6 permutations of 6 elements from S elements that are given to us. Given to us. Okay? Now, for each permutation, I'm saying permutation and not combination because the order of the numbers in the pyramid obviously matters. So for each permutation, here's what we're going to do. We will compute the number at the top. Compute score for the permutation, first of all, and let's initialize a max score up here. Initialize max score and best permutation. Best permutation. Right? So we compute the score for the permutation, and if the score of the permutation is bigger than the best score we have so far, update best score and best permutation. Finally, at the end, we're going to print out the best score and the best permutation. Print the best score, print the best permutation. Now, of course, I will attempt to code this up, but before we do that, let's try and understand how fast this algorithm will run so we can predict how many marks we're going to get on this problem. All right, fair enough. Let's do it. So let's go back to the actual problem description. And we'll take a look at the constraints here. So we know that B is less than 32,768. But obviously, B doesn't really matter, right? Because we are only looking at permutations, right? The reason why B is less than 32,768 is because we want to make sure everything is an integer. But that's not a big deal for us because we're using Python, everything is fine. Okay, so the next thing is the second line will contain an integer s representing the number of integers in your set from which the bottom row must be chosen. You are guaranteed that 6 is less than or equal to s is less than or equal to 32. So why is s bigger than or equal to 6? Well, obviously, if we only had 5 numbers to choose from and we had to pick 6, that wouldn't make any sense, right? And then the constraint s less than or equal to 32 is really what we have to worry about, okay? So we know that we can have up to 32 elements to pick from. So what is 32p6? So if we go back to our webcam, so what is the running time of this algorithm? So what is the running time? The running time of the algorithm. Right? What is it? So we know that there are PS6 permutations. And for each permutation, we are doing a constant amount of work, right? So we're doing inside the loop. Computing the score is actually very quick because it's just addition and multiplication and mod. So it's actually an O1 operation. And so is updating the best score and best permutation. That's really quick. So the running time is O of PS6, whatever this is. But we know that this is O of S, S minus 1, S minus 2, S minus 3, S minus 4, S minus 5. And obviously we can neglect the 1, 2, 3, 4, and 5 because we know that the leading term will be O of S times S times S times S times S times S, because S minus 1, 2, 3, 4, 5 is close enough to S that we can basically say that this is O of S to the power of 6, right? Close enough. So close enough. Okay? And what is 32 to the power of 6? How big is that? All right? How big is 32 to the power of 6? Let's actually calculate that. 32 to the power of 6. I'll write the number down. 32 to the power of 6 is 107374184. Okay? And what does that mean, right? What that means is that it's definitely not going to run in 50 million operations. Okay? Fair enough? So what I mean is, right, if we put some commas here, what this is about 1 billion operations. And we know that from like week 1, from our first workshop, hang on, let me adjust this. Whoops, other way. Yeah, so 32 to the power of 6 is this number. And because that's about 1 billion operations, and a computer can do 50 million operations per second, 100 million tops, but let's assume 50 million for this, right? We won't finish in time for S equals 32. However, if S is fairly small, maybe it's like 10, 15, 20, we can work this out. We will finish on time, okay? So we want some S where S to the power of 6 is less than 1 million. So we can solve that equation and we'll know how much we can deal with, okay? And it turns out that in the contest that this was set, a brute force algorithm like this actually scored about 60%. That's pretty good. That's not too bad. So if you came up with something like this, a way to be able to find all of these permutations, loop through them, and literally just check the numbers, you would have done okay on this problem. You would have been pretty happy. Okay, so now we've finished talking about this problem. Let's actually code this up. So let me get out Python and we'll get started. Let me just put a new window capture. So here we go. Okay, we have our Python terminal up. So let us get started. So let's call this stacking numbers brute force. Eventually I will tell you oh, it already exists. Probably because I've done this problem many times, or at least once before. But yes, let's actually code this up. So here's the idea. So we'll read the file, which is stackin.txt in this case. So input file, open stackin.txt. We'll read the base in. Okay. Now we're going to read the list of numbers in. So okay, we'll do this. So let's make a list. So our choices is a list. Let's do a nice list comprehension so we get everything out for I in input file dot readline dot split. So we have our 6 numbers, or our S different numbers, and these are all going to be our choices. So now here's what we're going to do. Let's make our best score and initialize it as -1, because clearly we can't get a score of -1. And our best permutation so far as an empty list, which will be filled in by 6 numbers. So to be filled in by 6 numbers. And what we want to do is we want to find the permutations. But this is actually really easy if we are allowed to use a particular package. So import, so from iter_tools, tools, import permutations. So if you know about this function, what it does is it literally takes permutations of a list and a number. So for example, I want the permutations of a list of 6 things with I want the permutations of a list of, say, 10 things, and I want the permutations of 6 things. It will essentially give you all of those permutations. So the idea is that what we're going to do is we're going to loop through all permutations. Loop through all permutations. We're going to say for k in permutations, choices 6. So what that means is it will take each permutation from all of those permutations, right? We have length of choices, which is S, permute 6 permutations. and it's going to pick each permutation from all of these. So we're going to have, let's make a list. So L equals list K. So this will come out as like some sort of tuple, so we'll just make it a list. So we'll go A equals L0, B equals L1. We'll just define everything. C is L2. In fact, we'll do it in a nice way. A, B, C, D, E, F equals L0, L1, L2, L3, L4, L5, just to save some lines. And now we will compute our score, which is A plus 4B plus 6 times C plus 4 times D plus E mod base times B plus 4C plus 6D plus 4E plus F mod base. So we multiply all of these things together, and if score is bigger than best score, then permutations, best permutation so far is A, B, C, D, E, F, and best score is score, right? And otherwise we do nothing. Make sense? And that's basically the entire program. All we have to do is write this answer to the output file. So what we'll do is output file is open stack out.txt. Obviously beware of bugs in this code. I've only proved it correct, not tried it. That's an old saying from Knuth. So yeah, please don't write this code out from scratch, write your own, but I'm just going to give you the idea. And we will simply write the answer. So output file write the best score. We'll write a new line. And of course, we will write the permutation, of course. So output file dot write there we go. Okay, so now we basically have what should be a working program that should solve the problem for, well, that should solve the problem at least for the brute force case, right? At least for all cases that can be solved by brute force. So now we know that we can get a certain number of marks on this problem simply by brute forcing the problem, right? By just trying all permutations of things, we were able to basically find an algorithm that was able to get us some marks. Even if it wasn't necessarily the best algorithm, it was still correct. It was still right. Even though it wasn't necessarily very efficient, it was right. And as we're going to see later on, the actual algorithm for this problem is a very clever modification of this brute force method. So we'll see that. And it'll be highlighted when we get to the section on divide and conquer. This will be a very important part of that, and I'll take the time to actually explain the solution. All right, so I think I will, wait, do I have time for one more? Yeah, okay, I have time for a little bit more. So let me go to another problem. Yeah, okay, I have a little bit of time, so let's go through one more example of this. Okay. Okay, here is a problem. Okay. The problem is Cameron and Jamie's kid is almost 3 years old. However, even though the child is more independent now, scheduling kid activities and domestic necessities is still a challenge for the couple. Cameron and Jamie have a list of n activities to take care of during the day. Each activity happens during a specific interval during the day. They need to assign each activity to one of them so that neither of them is responsible for two activities that overlap. An activity that ends at time t is not considered to overlap with another activity that starts at time t. So essentially we have a bunch of activities, and we need to assign them to two people so that none of the activities actually overlap. All right? So, for example, suppose that Jamie and Cameron need to cover 3 activities, one of them running from 1800 to 2000, which means 8 o'clock, another from 1900 to 2100, and another from 2200 to 2300. One possibility would be for Jamie to cover the activity running from 1900 to 2100, with Cameron covering the other 2. Another valid schedule would be for Cameron to cover the activity from 1800 to 2000, meaning 8 o'clock, and for Jamie to cover the other 2. Notice that the first 2 activities overlap in time between 7 and 8 p.m., so it is impossible to assign both of these activities to the same partner. Okay, so broadly, obviously, we read the problem very quickly, but broadly, the idea is that we have some intervals, and we want to assign them to two people such that there are no overlaps in either of the schedules. So obviously for n equals 1000, this is much more difficult than for n equals 10. But if there are only 10 activities, we can brute force it, which is what I did very, very quickly in the time I had when I was looking at this problem. So let me go to the code. Hope you can see this. Maybe? No. Okay. There we go. Okay. So in this case, what we want to do is we want to find all of the intervals. First of all, we get all of the intervals as input. And what we want to do is we want to basically just randomly assign them or assign them in every possible assignment that we can, and then just check if the intervals overlap. So for example, what we did is we can simply just try every possible way of assigning things. So for example, in this case, if we have n elements, we can try the power set of those n elements, which is like all subsets of them. So for example, if I have a set 1, 2, 3, I can just do 1, 2, 3, 1, 2, 1, 2, 1, 3, 2, 3, and 1, 2, 3. So let's assume that Cameron gets activity 1. Then Jamie is going to get 2 and 3. Or if Cameron gets 1, 2, Jamie is going to just get 3, right? So there's kind of it works out that whatever Cameron gets is whatever Jamie doesn't get. Whatever Jamie gets is whatever Cameron doesn't get. So for each, we can loop over everything in this particular set of n things, right? And we can just say, okay, let's say, assume this is what Jamie gets, assume this is what Cameron gets. Now we check all of the intervals. Do they overlap, right? It's not too hard to do this, right? In this case, what we do is we just check everything in Cameron's intervals and everything in Jamie's intervals, and we just check everything to see if they overlap, right? And if they do, then we try another assignment. If they don't, we are done, right? So if everything is good, if we can't find a good set that we can use, then the answer is impossible, so we can never do it. Otherwise, we know exactly what gets assigned. So this problem isn't that difficult if you consider it from the brute force perspective. But when n equals 1000, the brute force is untenable. So brute force can get us some marks, but not all of the marks. I hope that makes sense. So we basically learned today that like how we can use brute force to kind of devise algorithms that may not be the best for some problems when the problems are really hard, but they still might get you some marks, and they're still very useful. We learned functions like permutations and power sets that are really good for getting you all of the permutations of a list, all of the subsets of a list, because these are the sorts of things that you need to loop over when there are a large number of possibilities to choose from, right? Uh, Obviously, these may not generate the most efficient algorithms. And that's where kind of other techniques are going to come in, which we're going to talk about later on. But brute force definitely helps you. Okay, with that, I will end the session, and I'll see you everyone next Monday. See you around.